All right, this lecture we are going to cover ANOVA, analysis of variance, which is the same thing. As you can see, ANOVA is made up of the term analysis of variance. We have big A, big N, big O, big A, big V, or big V and big A. So ANOVA. What we're looking at here is a very simple concept that is a lot like the independent samples t-test. For an ANOVA, all we are doing is comparing the differences between the means of more than two groups. Sometimes people say two or more groups, and although that's accurate, I want you to think of it as more than two groups. The reason why is because when we have an independent samples t-test, we are using the differences between two groups. With an ANOVA, we like to reserve it for when there are more than two groups. That being said, you can do an ANOVA with only two groups and get the exact same answer. Conventionally, though, we use ANOVA with more than two groups. So when we do use two groups only and perform an ANOVA, the results are the same. The output looks a little bit different because the way to calculate it is different, even though we arrive at the same conclusion. So analysis of variance is a design where we are looking at the difference between more than two groups, and each of those groups has different people in it. That's why we call it a between subjects design. So a between subjects design means that we are looking at three different groups in this case, or more. It could be 10 or 15 or 100, doesn't matter. But we're looking at the difference between the subjects to see if there are differences between those three groups, as opposed to a situation where we would have the same group repeated 3 times in a row on some kind of measure. We are not doing it within subjects, we are doing between subjects here. Even though they are conceptually very similar, the way to calculate a different kind of ANOVA where we're looking at the same group 3 times, it's pretty complicated, so it's not something that we cover in this course at all. Let's go ahead and jump into the research questions and hypotheses for an ANOVA. And there are a couple of quirks about the hypotheses, especially compared to other hypotheses, but I think that will be okay. And something else that I also want to tell you about is that we are not going to do this by hand for any kind of assignment. We are going to walk through an example where I show you the hand calculations just because it's important for you to be able to see how it works mechanically. I hope that you pick something up from it. I hope that you're able to follow along, but realize that if you don't follow along with it, if you're just not quite getting it, that's okay. We're going to look at the concepts, and the most important part is that you're able to logically work through the hypothesis testing procedure and make sense of the SPSS output. That's the most important part, even though the hand calculations are also important. So, an ANOVA really only has one research question. We really don't think about one-tailed versus two-tailed ANOVAs, and I'll tell you about that when we get to talking about the F ratio. But the research question for an ANOVA is there a significant difference between the means of more than two groups? So is there a significant difference between the means of more than two groups? By the way, between is logically, or not logically, grammatically incorrect. Normally we say among when we're talking about more than two groups, grammatically, but for statistical lingo, we use between even when we're talking about more than two groups. So that's just something that we grammar police need to be aware of. So is there a significant difference between the means of more than two groups? The research and null hypotheses need special attention because the wording and symbols are slightly different. So the alternative hypothesis is this: not all of the means are equal. So if we have 3 groups, the alternative hypothesis is that at least one of those groups is significantly different than the others. That's all we can say about it. We can't say that the groups increase at each step or decrease in each step significantly. All we're saying is that there is a significant difference somewhere. If you had 3 groups, for example, Group 1 could be equal to Group 2. Group 2 could be different than Group 3 significantly. Or Group 1 could be different from Group 2 significantly, but Group 2 could be equal to Group 3. So we have to look at any kind of significant difference that occurs anywhere in the model and we can't suggest that it's going to increase or decrease like we have been able to when we looked at the independent samples t-test or the single sample t-test or the dependent samples t-test. If you look at the conventions, we say that the mean of group 1 is equal to the mean of group 2, which is equal to whatever group all the way to the last group. This is a convention that we use, the ellipses, that says that there is skipped information or missing information. So basically what this means is that for any group that you have all the way to the last group, they're all the same. So if you think about it logically, like the rest of the null hypotheses, all we're saying is if all of those groups are equal, then that means there is not a significant difference. Makes sense. However, when we are working in step number 5, when we're talking about seeing if our samples score is significantly different than the population score, we use a different kind of way to compare the scores. So in the case where we are testing to see if our samples F score, which we'll talk about in a little bit, is different than the populations, what we want to know is our sample score less than or equal to the population's F score? So our sample score, is it less than or equal to the cutoff score? Remember, when we talk about populations, we're generally talking about the comparison distribution, and that is the group that we're using to compare our sample score to. So our comparison distribution for an ANOVA has a certain cutoff, and we want to compare our sample score to see if it is significantly different than the cutoff. Okay? But the null hypothesis is tested using this inequality. Is the F score of the sample less than or equal to the F score of the population? That'll make more sense a little bit later on. Let's take a look at some of the differences between a t-test and an ANOVA. In this case, we are using just some dummy data. It's not important what this data means necessarily, but I want to show you what the differences are. And I'm using a very simplified version of some data. And the data that we're going to be using just for this slide only, by the way, because we're going to move into an example from the book later on in lecture. But in a t-test, we want to know if there is a significant difference between the means of two groups. Let's say that we have some kind of depression rating on a score of 1 to 10, where 1 is very little depression and 10 is a lot of depression. Okay? A 10 milligram dose of some drug, it doesn't matter what it is, for 5 people have these depression scores. A 50 milligram dosage of some depression medication has these scores. It looks like they go down. We're not going to calculate it, but it looks like there is a significantly lower mean for the people on the 50 milligram dose compared to people on the 10 milligram dose. This is a independent samples t-test. Is there a significant difference between two groups? For an ANOVA, all we're doing is adding a third group somewhere, or more. You can have as many as you wanted to. So for this example, I left the 2 lower groups the same and added a 100 milligram dosage to see if having a 100 milligram dose of this medication made a difference somewhere. And again, this is just some dummy data, and maybe there's a significant difference there, maybe there isn't. But the idea is that we can take the mean of each of these groups and compare them to find out if they are significantly different than one another. And all we have to do for an ANOVA in order to reject the null hypothesis is find a significant difference anywhere between these 3 groups to see if there's, for example, it could be between 10 and 50, it could be between 50 and 100, it could be between 10 and 100. All we're interested in seeing is there a significant difference anywhere? And this is the big difference between the t-test and the ANOVA. Another idea that we have to be careful to pay attention to is the idea of within versus between. I know these look like scary ghosts, spooky, right? But what we're talking about here is these are 3 different groups, and they're represented here by some kind of curve that has a mean, a standard deviation. It doesn't matter what they are. These are just demonstrations. When we talk about within groups, we're talking about each group has its own mean and its own spread of scores. Okay, so that's the case for group 1, group 2, and group 3. With ANOVA, we want to know, first, is there a significant difference between the means of these groups? So are these groups far enough apart from one another to be considered significant? Also, we want to know how spread out these scores are within themselves. Okay, so within each group, we have the spread of scores. And between each group, we have differences between the means of the three groups. Ideally, in order for an ANOVA to have a significant result, we would have means that were far apart from one another, meaning that the three groups are not close to one another, meaning that they are significantly different. And the amount of variance within each group would be relatively small so that these curves weren't so wide that even though their means are far apart, the curves widen out and overlap each other. Okay, so between groups, we're talking about what is the amount of variance that each of these three groups has in terms of their means, how far are their means away from one another, and within is how much variance is within each group itself. Here's a couple of examples of comparing between and within. So let's look at this top right example. In this top right example, we have three groups of people that all have means and the spread of scores is something. In this particular case, we have three groups that have means that are relatively close to each other. Again, it doesn't matter what the actual spread of those means is. We're just looking at it graphically to kind of get an understanding of it. So these three means are relatively close together, and the spread of scores appears to be normal, and it should be. These are three normal curves. So in these cases, there doesn't appear to be much of a significant difference between these three groups. Let's say that these were three medication levels, and it looks like these three medication levels don't significantly vary from one another. This is just based on our visual interpretation of it. The top right-hand example has three curves that are the exact same shape as in the prior example, but the means are farther apart. So in this case, it looks like that because these means are so far from one another, there appears to be a significant difference between them somewhere. Now, probably there is a significant difference between the first group and the third group. And that's because these two means are so far apart from one another. It's hard to tell, but there may or may not be a significant difference between the middle group and the two outside groups. Again, there are no numbers here, and we're just looking at it graphically as an estimator, so it's not important that we see the exact differences. But just looking at this, we understand the idea that these three groups are far away from each other, which might cause some kind of significant difference. What is also good about this distribution that might support the alternative hypothesis is that the spread of each group is fairly narrow, meaning that the spread of the groups means that they're less likely to overlap each other. So if these three groups don't overlap each other by much, then we're probably going to support the null hypothesis and reject support the alternative hypothesis and reject the null hypothesis. The bottom example has a mixture of things. We have two groups on the left-hand side that appear to not be different from one another. And then we have a group all the way on the right that is farther away from the two on the left, but look at the spread of this group. I'm going to pull this group up a little bit so that you can see how spread out it is compared to the other ones. Oops, wrong one. Put that back. So this group has a wider spread, okay? And that was done intentionally. So the group that has the wider spread means that it has more of a likelihood of overlapping the other curves even though the mean is farther away. So in this case, we have a lot of variance inside of this group. That means that the scores are not tightly packed around the mean. There's a lot of variance there. If there's a lot of variance in this curve, then it allows an overlap to happen over these other two that seem to be farther away. Even though the mean of this group is farther away, meaning that the between mean is farther away, the within variance is so spread out that it overlaps a large part of both of these other curves. And in this case, even though the means are farther apart, we're probably not going to have a significant difference. This is the case again in the bottom right-hand demonstration, where we have two curves that have fairly wide spreads on them, and even though they're farther apart from one another, the spread of these scores overlaps so much that it's probably not significant. Now, the curve all the way to the right probably is going to be significantly different than the one all the way to the left, but maybe not from the one in the middle, because the one in the middle tends to overlap the curve on the right by quite a bit. So when we talk about between and within, we have to remember that the between amount of variance is the amount of variance that occurs between these three means. And the within variance is the amount of variance that occurs within each group. In the top, all of these appear to have fairly small within groups spread or variance, but in the bottom, especially in the bottom right-hand one, the amount of within group variance is pretty wide, pretty large. A fairly easy thing to understand is the degrees of freedom within versus degrees of freedom between. It's fairly simple. Degrees of freedom typically n minus 1. We know that from chapters 7 and 8. The degrees of freedom within is equal to the degrees of freedom in the first group plus the degrees of freedom in the second group plus the degrees of freedom in every group through the last group. So in this case, it's n minus 1 plus n minus 1 plus n minus 1. If there were 5 people in each group, you would have 5 minus 1 is 4, plus 5 minus 1 is 4, plus 5 minus 1 is 4, 4 plus 4 plus 4 would equal 12. That would be the amount of degrees of freedom within. So whenever you need to figure out the amount of degrees of freedom within, you just find the amount of degrees of freedom in each group and add them together. Degrees of freedom between is even easier. The degrees of freedom between is equal to the number of groups that you have minus 1. So if there are 3 groups, the number of degrees of freedom between is 2. Not a really hard concept. I hope that doesn't trip you up too much, but it is important so that you can figure out what to do in terms of finding a critical value or the cutoff value. The F ratio is the meat and potatoes of this lecture in terms of how to understand why we are comparing the amount of variance between and the amount of variance within. The estimated variance between the groups is fairly easy to figure out, but it does take some careful plugging in of information. But here's what we're talking about when we're talking about the population variance between the groups. We are talking about finding out how much variance there is between the means of the groups. So just listen to this sentence for a second. If we have 3 groups and they all have their means, let's say one group has a mean of 4, one group has a mean of 5, and one group has a mean of 6. You can find out the average of those 3 means, okay, by adding those 3 means together and dividing them by the number of means, which would be 3 in this case. And then you could calculate how much variance there is between those means. You could find out how spread out those means are. So essentially, you could calculate the average distance between those 3 curves, like we observed in a couple slides ago. And then what you can do is you can then calculate the variance of the means of those groups. So the variance of the means of the groups is what's known as the estimated population or the population variance between. The population variance within is actually quite simple as well. All we're doing is we're finding the average amount of variance that each group has. So we know that group 1 will have some kind of variance in it. We know that group 2 will have some kind of variance in it. And we know that group 3 will have some kind of variance in it. Once we find out what the total amount of variance is in those 3 groups by adding them together, we can divide it by the number of groups, and that gives us an average amount of variance that each group has. That's all we're doing with the variance within. That one's pretty easy to calculate once you have your data, and the between population variance is also relatively easy, but it takes a little bit more care to make sure that you're conceptualizing things correctly. So let's look at what this means. If there is no difference in the variances between the groups, meaning that the means are not very far apart, and the within groups variance, meaning that the variance within the groups is relatively small, then the F value would be 1. So if all of the groups perfectly lined up with one another, then the F value would be 1 because there would be no variance between the groups and very little variance within the groups. So we would have a very small number, probably close to 1. By the way, we can have an F ratio that's less than 1, but it's very unlikely. It happens largely when we have small samples. So again, if we have 3 groups of individuals that have similar means and relatively small within groups variances, the F ratio would be close to 1. And that would mean that there is really no difference between them. Whenever we have an F value that's really low like that, we're going to reject the null hypothesis. Pardon me, that was incorrect. We're going to fail to reject the null hypothesis. Sorry, I was reading something different. It threw me off. Let me repeat that. If we have an F value that is close to 1, that is a failure to reject the null hypothesis, meaning that the 3 groups are similar to one another. If there are significant differences, what that usually means is that we have means that are spread out from one another, meaning that we have between variance. Okay, the variance between the groups is great, meaning that the means are spread out from one another. And generally, the within groups variance still remains about the same. Generally, that doesn't change a whole lot. That means that we're going to have a big number on top, a little number on the bottom, and we have a big number on top, a little number on the bottom, and divide it. That gives us a number that's going to be much larger than 1. Okay, so just kind of speaking to that point, if we have a lot of variance within each group, what we're talking about is that there are lots of individual differences in the group, meaning that the people who we asked to take whatever, if it's medication, for example, that there was a lot of variation in the people themselves who took the medication, as opposed to the medication doing something important. So we were looking to see if there is a significant F value. Generally, it's going to be much greater than 1. Usually it starts in the upper 2s is when we start to find significance, but we'll take a look at how we actually do that based on an example we're going to look at. But we want to find out if there is a significant difference between the groups compared to how much variance is within the groups. Don't be shocked, but here comes a slide where we kind of break down the formulas for these. There it is. Let's take a look at this byte by byte, because really none of this is anything different than we've ever looked at before. And as a matter of fact, calculating it's a little bit easier than some other things. But this is just a concept level of how these formulas work together. So again, we're not going to put numbers to it at this moment. We'll do it a little bit later on. But this is what the construct of the formula looks like. We have the mean, and that's the mean of each group. Okay, so if we have 3 groups, for example, each group will have a mean. We know how to do that. That's fine. We have this thing called the grand mean. And the grand mean is pretty easy. You take the sum of all the means that you have in your group. So if there are 3 groups, you take the 3 means, add them together, divide it by the number of groups, and that gives you the overall mean for all of your groups. No big deal. It's a piece of cake. Now, the first thing we do once we have this information is we need to calculate the amount of variance between the groups. That is, how much variance is there between those 3 means? Well, we do that by taking the sum of the mean minus the grand mean squared. Now let's not get too bent out of shape over this formula. This formula is exactly what our variance formula looks like when we were doing it way back in chapter 2 even. Good gravy, it's a long time ago. This is the same kind of formula. It is the sum of some number minus another number squared divided by n minus 1, or the degrees of freedom between. This is pretty simple. We take all of our means, we subtract the grand mean from it, then we square it. We do that for every mean, then we add them together, then we divide it by the degrees of freedom. The degrees of freedom between is the number of groups minus 1. We're going to look at an example of how to do that later, so I'm not going to belabor that right now, but this is a fairly simple thing to be able to do. Okay, so this is the variance of the groups this is the variance of the means of the groups. And once we have found the variance of the difference between the groups, we multiply that variance by the number of people in each group. And in this example, we used 5 people from the medication example. So each group had 5 people in it. So you would multiply what you found in the estimated population variance of the distribution of means for the means. It's an odd way of saying it. We would take that figure and multiply it by little n, which is number in each group, not the number of groups, big N. And that would give us the amount of variance between each group. We save that. And then we calculate the amount of variance within each group, which is pretty simple. For each group, we had 5 people in each group. We can calculate the variance of those by taking each score, subtracting the mean from it, squaring that, adding it together, and dividing it by n minus 1. We can do that. Each group has its own variance. The variance in group 1 plus the variance in group 2 plus the variance all the way through the last group divided by the number of groups, which gives us the average amount of variance in each group. So that gives us the estimated population variance within each group. So that gives us the bottom half of our ratio. And once we have the top and the bottom, we calculate it, and it gives us an F ratio. So to put it into plain-ish language, the F ratio is the variance of the means of the groups. I'll say it slower. The variance of the means of the groups. So we found out on average how far each mean is away from the other. And then we divide it by the mean of the variances of the groups. I promise I'm not trying to trick you. The mean of the variances. Remember, we took the variances, then we found the average of the variances. And that is the mean of the variances of the group. So on average, what is the variance of each of the groups? Once we have that, again, we can calculate our F ratio. You may be asking yourself, great, we have an F ratio. What do we compare it to? Well, we have a new table that we're going to use in order to find out how to determine if our sample is significant. Up until now, we've been looking at comparison distributions that are symmetrical, that normal curve that we look at. And we're looking at differences above or below the mean to determine if there are significant differences in either direction. Well, with an F ratio, which is what we use when we are talking about ANOVA, generally we can't have negative numbers. It's impossible to have a negative F ratio because when you sum the squares, way back in any step where you're looking at the variance, you get rid of negative numbers. So you will always have a positive numerator and a positive denominator, so you can't have any denominator or numerator less than 0. So when we have an F ratio, we are comparing it to a distribution, where we have, where's my pen? Where we have a starting point of 0, meaning that the ratio of variances within and between F is equal to the amount of variance between and the amount of variance within. When we have this kind of situation going on, we're looking at a ratio that gives us a number greater than 0 and usually less than 10 or 20, I suppose, depending on your sample size and everything. But we have a distribution to where we still have standard deviations away from the mean. But they're always positive. Generally, what we are doing is comparing our situation to 1. If we had an F ratio of 1, then that means again that we have as much variance between the groups as we do within the group. So any number divided by the same number is 1. So this is kind of a null is true situation. And a null is true situation happens all the way up until the alpha level. And then we have a situation where we begin to support the alternative hypothesis. So we failed to reject when our sample's F score is less than our alpha, and if it's greater than our alpha, then we reject the null. Okay? And I'm going to erase this just for the sake of clarity. Maybe I shouldn't have been up there in the first place. So we reject the null hypothesis when our sample score is above this, meaning that the amount of variance between the groups, that is how spread out the means are, is a lot greater than the amount of spread within each group. If that's the case, then we have a big number on top, little number on the bottom, and that gives us a situation where we have a significant difference between our ratio, or in our ratio. Okay? So the F table is what we use. What's interesting about an F table is that as you change the degrees of freedom, the shape of the comparison distribution changes. It's a pain in the butt to really describe why that happens. It's mathematical in nature, but it just, if you must know, this is the way that an F distribution changes shape based on the number of degrees of freedom. So for degrees of freedom of between subjects and within subjects, if you have 1 degree of freedom and 1 degree of freedom within and between, then the distribution looks like this. If you have 2 and 1, then it looks like, that's the black line, then it looks like this line. The blue line looks kind of like this, which is what ours looks like in our example where we have 3 groups, 3 groups of people with 5 people in it. It looks a little bit different, but it's close because this is a 5 and 2, ours is a 5 and 3. So the shape changes with every distribution. Now, what is interesting though is that if you have a lot of people, so if you had 100 people and 100 groups, so if you had 10,000 people, is that right? If you had 10,000 people, then you would have a shape that looks almost like a normal curve. I say almost because it begins at 0, but it goes infinitely to the right. So it is obviously a positively skewed curve. But the shape changes. What's okay about that is that we don't really need to compare our results to any particular shape. We're going to compare it to an actual cutoff score. So the shape doesn't matter. The score matters, and so does the probability level. But if you must know, this is how the shape changes based on the amount of degrees of freedom within and between. Okay, back to reality. So the way we use an F table is this. You find it in the back of your book, and it's after the T table. So you look after the T table, it has an F table, and you need to know 2 bits of information. You need to know the amount of degrees of freedom between, which is the number of groups minus 1, and you also need to know the degrees of freedom within, which is the number of people in each group minus 1. So if you had 3 groups of 10 people, let's say, the degrees of freedom between would be 2, because that's 2 groups minus 1. The degrees of freedom within, what did I say, 10 people, would be 9 plus 9 plus 9 is 27. So the degrees of freedom within would be 27. I'm pretty sure I said 3 groups of 10. If I didn't, I messed up and I recovered with the 10. And we also need to know what our alpha level is. And remember, we're going to generally use a cutoff alpha level of 0.05. So here's an example. If we had 3 groups of 6 people that were in a study and we want to see if their scores are significant at the 0.05 level, what are the answers to numbers 1, 2, and 3? Well, the numerator degrees of freedom is the same as the degrees of freedom between. Remember, the numerator is on top. That's the top number. Degrees of freedom between is the number of groups minus 1. 3 minus 1 is 2. The denominator degrees of freedom is the degrees of freedom within, which is the number of people in each group minus 1. So there are 6 people in each group. That means that each group has 5 degrees of freedom. 5 times 3, or 5 plus 5 plus 5, is 15. Okay. And if you wanted to know what the significance of that was, you could flip back to your F table, and you could find where the intersection of let's see, denominator degrees of freedom, that is, what did we come up with? 5, 10, 15 degrees of freedom in the denominator at the 0.05 level. and 2 degrees of freedom in the numerator. The cutoff alpha level is 3.68 according to the table in the back of the book. That's 15 degrees of freedom in the denominator, 2 degrees of freedom in the numerator, and at the 5% or 0.05 significance level. That's 3.68. That's what our cutoff F value would be if we were going to conduct a study like this. So let's hop into an example. I know we've done an awful lot, but let's hop into an example, and that will take us through the end of the lecture. And we'll have to pick up post hoc testing when we do the data analysis, because that's when it's most appropriate to talk about that, I think. So 15 people were selected to perform a study where they rated a situation involving a woman passing bad checks. She was either falsifying the check or she didn't have money in the account, and for whatever reason, her checks were bad, but she was writing them anyways because she needed to pay the bills or whatever. They were to rate her level of guilt on a scale of 1 to 10. So these 15 people all rated this woman's level of guilt on a scale of 1 to 10 based on the knowledge that she had written some bad checks. The 3 groups were told something different about the woman in the scenario. One group was told that she had a prior criminal record. One group was told that she had a clean criminal record. One group was told no other information about the woman, and the data is below. So in the criminal record group, the first person said that she looks like she had a guilt of 10. Second person had a guilt of 7, third 5, fourth 10, and fifth 8. In the clean record group, these are the numbers that follow, and then the no record group. So each person, 15 people in all, rated this woman's level of guilt based on the information they had regarding whether or not she had a criminal record, a clean record, or if there was no record information available. We're going to work with these figures in this example. These also follow along what's in the book, so you can check on that to see if it makes sense to you. Step number 1, we need to identify the populations, and we need to develop a research question too, and then come up with the null and alternative hypotheses. So population 1 in this case, we could call that the criminal record group. So the mean of the people that knew that she had a criminal record group. The population 2, we can call that the clean record group. So that'll be the mean of the clean record group. And then population 3, that can be the mean of the no record group. Okay, no record. Maybe I call it something different later. Let me check. Nope, I'm good. So the research question for this ANOVA is there a significant difference? I mean, I'll write it down below. Is there a significant difference between any of the groups or any of the means? Good research question, even if it goes uphill. So the alternative hypothesis is very simple, but it is not all means are equal. That means that somewhere there are 2 means that are not equal. And we know that we mean significantly different. And here, for the null hypothesis, it's that all the groups are equal. So the mean of the criminal record group is the same as the mean of the clean record group, which is the same as the mean of the no record group. What's interesting though, and we talked about this before, what we're testing here is to see if our sample score, remember our F ratio, we want to know, and this is what the null hypothesis, if the null hypothesis is true, the F score of our sample will be less than or equal to the F score for our cutoff of our population. So it's our population, which is based on our cutoff. Remember, we looked at the cutoff score here. So we want to know if our sample cutoff score is in this reject null situation. And if not, then we fail to reject the null hypothesis. So this is the inequality we will test in order to determine if there are significant differences. This is what we'll test in step 5. Test in step 5. So far, so good. Step number 2. Generally in step number 2, we have to do an awful lot of work. But in step number 2 for an ANOVA, when we are looking at what the comparison distribution is, we're really just looking at that curve to determine if our ratio is significantly different. So really, our comparison distribution is that F distribution that's based on the degrees of freedom between, degrees of freedom within. And remember, the shape of the comparison distribution changes based on the degrees of freedom. It's not important that you understand why well, I would love you to know that, but that's beyond the scope of this class. But we are just going to understand that the shape changes, and it's not important really at this moment why or what the mechanism is. But we are going to be using that comparison distribution, and we want to know if our sample's cutoff score is significantly greater than the population score. I said sample cutoff score, I meant sample score compared to the population's cutoff score, pardon me. Step 3, we need to find out what the cutoff F ratio is. And we do that by consulting our F table. And the way that we do that is we calculate the degrees of freedom between, the degrees of freedom within. By the way, degrees of freedom between are the numerator. And then degrees of freedom within is the denominator. Look at that, fit right in there. And we also know that we're going to use an alpha level equal to 0.05. That's kind of our convention. When I consult the F table in the book, I'm looking for the row that has denominator degrees of freedom. In our example, we have 15 participants altogether in 3 groups. Okay. So our between subjects degrees of freedom is equal to n groups minus 1, which is equal to 3 minus 1, which is equal to 2. So my numerator degrees of freedom is equal to 2. The denominator degrees of freedom is the degrees of freedom in group 1 plus the degrees of freedom in group 2 plus the degrees of freedom in group 3, which is equal to 4 plus 4 plus 4, which is equal to 12. So my between degrees of freedom, or my numerator degrees of freedom, is 2. My degrees of freedom within, or my denominator degrees of freedom, is equal to 12. So I find the row that says denominator, or excuse me, the column that says denominator degrees of freedom. I go all the way down until it says 12. And then I use the row that says 0.05, because that's my significance level. And then I find the column that matches my numerator degrees of freedom. And in this case, it's 2. For an alpha level of 0.05, degrees of freedom between, which is my numerator, equal to, 2. Degrees of freedom within equal to 12. My cutoff is equal to 3.89. 3.89. So on my F ratio, my F distribution, 3.89, which is kind of more or less where this alpha level is for the demonstration anyways. If my F ratio of the actual sample is greater than that, then I can reject the null hypothesis. If it is less than that, then I fail to reject the null hypothesis. So step number 3 is complete. Boom. Step number 4, and by the way, we'll make sure we come back to that later when we actually do the test. Step number 4, we're going to do a little bit of calculating. And I've done a little bit of the work already because I don't think that we need to go back and do hand calculation of sample, standard deviation, and variance. We can do that, hopefully. So we need to calculate the F ratio, which is what step number 4 is, to calculate the sample's statistic. So we need to calculate the F ratio based on the variances within each group and the variances between the groups. Now, I'm going to show you the longhand of how to figure it out. Again, it is not critical that you can do it by hand. If you can follow along and you can make sense of it, awesome. That's cool. If not, it's okay. I need you to be able to understand the process in terms of just what it looks like we're doing, as well as being able to figure it out when you have your SPSS output in front of you so that you can make a decision for hypothesis testing. So I have those scores for each group. I also have the mean of each of these groups. So the mean criminal record score is 8 for guilt. It's 4 for the clean record, and it's 5 for the no record group. The sum of squares, which is when I added up all those scores, or excuse me, when I took all those scores minus the mean, squared them, and added them together, I got 18, 20, and 26. In order to get the population variance, I took 18 and divided it by the degrees of freedom. So 18 divided by 4 is 4.5. Remember, the only step between sum of squares and variance is dividing it by the degrees of freedom. The clean record group, 20 divided by the degrees of freedom. There are 4 degrees of freedom. 20 divided by 4 is 5. Same thing for the no record group. 26 was the sum of squares. 26 divided by 4, which is the degrees of freedom for that group, equals 6.5. I also calculated the grand mean. And the grand mean is the mean of 8 and 4 and 5. So 8 plus 4 plus 5 divided by 3 equals 5.67. That is the grand mean. And those figures are all going to be helpful in helping me to determine what the actual amount of variance is between the groups and within the groups. And we're going to plug it into the formula 2 slides from now. But first, I want to remind you what we are doing in in the rest of step 4. So remember, all we're calculating is what is the difference between the 3 means and what is the amount of variance within each group on average. That's all we're doing in this next step. It looks a little bit cumbersome, but it's okay. All we're doing is these 2 steps. On the next slide, we're going to be calculating the amount of variance that occurs between the 3 groups. And then on the slide after that, we're going to look at the average amount of variance that happens within each group. So, part 1, the estimate of the variance between the groups. That is, how much variance is there between the means of the groups. We're going to do this in a couple of steps. The first step that we're going to do is find out the estimated population variance of the distribution of means. I know that we haven't been really talking much about what the distribution of means looks like for this, but just trust me, this is what we calculate in order to determine what the estimated population variance between the groups is. So we're going to do that step first, and then afterwards we'll bring down the number of people in each group and multiply that by what we found for the for the estimated population variance. So the first thing that we do is we're going to take each mean and subtract it from the grand mean. Then we're going to square it. So the first mean, the mean of group number 1 was 8. This is the criminal record group. And we found that the average of the means of those groups was 5.67. So that means, I'm going to flip back a second. That means that the average of 8 and 4 and 5 was equal to 5.67. So we take the first score, subtract the mean of those scores. Take the second score, so this is the score of group number 2, the mean of group number 2 minus the mean of all the groups. And then this is the mean of group 3 minus the mean of all the groups. So when we subtract that, the first group, we get 2.33. We get negative 1.67 for the second group and negative 0.67 for the third group. Remember, these are our deviation scores. The mean of the first group is 2.33 above the mean. The mean of the second group is 1.67 below the mean. The mean of the third group is negative 0.67 below the mean. Well, it's 0.67 below the mean, or it's a negative 0.67. Then we square these. When we square them, we get 5.43. This is our variance. No, that's not, that's not our variance. That is just the square deviation score. So 5.43 is a square deviation score for group 1. 2.79 is a square deviation score for group 2. 0.45 was the square deviation score for group 3. Now, the next step is to add those together. Remember the sum of. So we're taking the sum of the square deviation scores, and that equals 8.67. So 5.43 plus 2.79 plus 0.45 is equal to 8.67. The next step is to divide it by the degrees of freedom. And we're talking about the degrees of freedom between. We calculated degrees of freedom between as the number of groups minus 1, and that is 2. So 8.67 divided by 2 is equal to 4.34. Now, this asterisked part is totally optional. If you want to plug your ears for the next 10 seconds, you can. Some ANOVA tables, well, all ANOVA tables that SPSS produces will provide something called the sum of squares between. That is the sum of squares between the groups. All you do is you take 8.67, which is the sum of squares, and then you multiply it by the number of people in each group, which in this case was 5, and that gives you sum of squares between. This is because you're going to see a number that you're not going to find in our calculations here. That's where it came from. Okay, back to reality. Once we have our 4.34, which is our variance of the distribution of means, we multiply that by the number of people in each group, and that gives us the estimated population variance between the groups. Okay, so when we do that, we get the numerator in our ratio, 21.70. So the variance between the groups is 21.70. Now, the next step is to complete the bottom of the ratio. By the way, I carried forward what we just found in our our estimated population variance between the groups, 21.70. The next step is to find out the amount of variance within each group and find out what the average variance is within each group. We found the variance of each group back here. I calculated it and then plugged in the numbers here. Again, I'm trusting that you could do that on your own. But the estimated population variance for each of these groups is listed here. I bring those forward to this part of the equation, because all I'm looking for is the variance of group 1, variance of group 2, plus the variance of all groups to the last one. In this case, it's 3. Then I divide it by the number of groups. That gives me the average amount of variance in those groups. 4.5 plus 5 plus 6.5. So I'm taking all the variances and adding them together to find out what the total amount of variance is. In this case, it's 16. Then I divide that by 3, which is the number of groups. 16 divided by 3 is 5.33. So there are 5.33 units of variance on average in each group. I'll say it again. There are 5.33 units of variance on average within each group. So the estimated population variance within is equal to 5.33. We bring that down to the denominator in our equation and we get an F ratio. The ratio of variance between the groups to the amount of variance within the groups is 21.70 to 5.33, or 21.70 divided by 5.33. That gives us an F ratio of 4.07. What this means is that there is a greater deal of variance between the groups, meaning that the group means are far apart, and there is relatively little variance within the groups, meaning that we have groups that are spread out far apart from each other, and their curves are not so wide that they overlap greatly. That gives us an F ratio of 4.07. The question is that a significant F ratio? We know that it wants to be much greater than 1, but is this much greater enough from 1? Step 5, we want to know if there is a significant difference between the F ratio of our sample compared to an F ratio where there are no differences between the variances within and between the groups. If the variances between and within the groups is the same, then the F ratio would be 1. Our ratio is equal to 4.07. We want to know if our ratio is significantly different than an F ratio where the variances would be the same. In step 3, we determined our cutoff score. Our cutoff score was 3.89, and that is what we found, or what we looked at here. Again, for the sake of demonstration, I had just put the alpha level at 4, but our alpha level is kind of pretty close to that anyways. So we want to know if our samples F ratio is significantly different than a cutoff F ratio. Our cutoff F ratio was 3.89, which is what we found in this step. Our cutoff F ratio was 3.89, or our alpha ratio. Our samples F ratio was 4.07, and again, we brought this forward from step number 1. Is our sample F ratio less than or equal to our population F ratio of 3.89? This equation is not true. 4.07 is not less than or equal to 3.89, therefore we reject the null hypothesis. So here's what we rejected. We compared the guilt rating scores of 3 groups of individuals. These 3 groups of individuals were told one thing each about the woman who was passing bad checks, either that she had a criminal record, a clean record, or that they knew nothing about her record. The null hypothesis was that there would be no difference between all of the groups. Another way of saying that is that our samples F ratio would be less than or equal to the population cutoff. We found that there was a significant difference between the ratio of the degrees, of the variances between and the variances within. There was a significant difference. These results indicate that we reject the null hypothesis and we support the idea that there is a significant difference somewhere among those 3 groups. That is it. Now, there is one small issue. That is, we have a significant difference somewhere, but where is it? Well, when we have a significant result, and only when we have a significant result, we need to find out between which groups there is a significant difference. And we do that by using a post hoc test. We're going to use SPSS to calculate it when you look at the data analysis demonstration. So for now, we're going to look at the idea behind the post hoc test, and then we will rely on the other video to make sense of it. If we conduct an ANOVA and we find no significant differences, that is, our F ratio is less than our cutoff F ratio, or our sample F ratio is less than our cutoff F ratio, then we failed to reject the null hypothesis and the study is complete. We have found no significant differences. If we find a significant difference, then we have to run a post hoc test to determine where the differences are. What that means is that we have to track down between what groups there are differences. In this example, we have 3 groups. We know that there is a significant difference between at least 2 of the groups, but we can't be sure which 2, and we can't be sure if it's only 2. We use what's called a pairwise test that determines the significance of each pair of groups. Here's what it looks like. If we have 3 groups, group 1, group 2, and group 3, we're going to compare group 1 to group 2, group 2 to group 3, and group 1 to group 3. So what we've done is we've looked at the 3 ways that we could find differences. So we could have a difference between group 1 and 2, between 2 and 3, and between 3 and 1. But we don't know where those differences are based on what we have. We have to do an additional test. It's called pairwise testing. So each test is compared. What's interesting is that these are done using what equates to a t-test. So the SPSS is going to run 3 simultaneous t-tests to find out if there are significant differences. Now, what I will tell you is that in SPSS, it will test actually 1 to 2, 2 to 3, and 3 to 1, but in SPSS, it will also do 2 to 1, 3 to 2, and 1 to 3. By the way, these are the same. They're just inverted. SPSS does it both ways because it likes to do commutative processes. It's okay, it doesn't matter. It will give us more information than we need. So it will do 1 to 2, 2 to 3, and 3 to 1, as well as 2 to 1, 3 to 2, and 1 to 3, even though it's redundant. So we're going to take a look at what that looks like in SPSS. But for now, we have conducted our formal test to determine if there is a significant difference between those three means, and the answer is yes, there is a significant difference between the means. Our next task now is to find out where those differences are.